Good evening, everybody. Welcome to day one on week 7 of the semester. The last thing that we mentioned before the weekend was the whole idea of naming alkenes. And if we have a name for the alkene, how do we draw the condensed structures versus the skeletal structure? Okay, so remember that whenever we're going from name to structure, we must start at the end. So let's just at least practice with the last problem that we have here. The name that was given to us is 3,4-dimethyl 2-hexene. So because the last word is hexene, then I know I have 6 carbons in my alkene. Then the position, the number 2, gives me the position of my carbon-carbon double bond. As you can see, based on the name, I have 2 substituents. 1 on 3 and 1 on 4, which are CH3 groups because they are called methyls. And then for my condensed structures, I need to fill in the hydrogens for each one of the remaining carbons. Okay, so let's review pretty quick how many hydrogens we need to add to the system. So carbon 1, let's put it on the chat. How many hydrogens will it get? Excellent, it needs 3. How many on carbon 2? Since it has 3 lines already. Excellent, it needs 1. What about carbon 3? How many hydrogens will it get? I like those zeros. Yes, 0, because it already has 4 lines. How many on carbon 4? Great. What about carbon 5? Awesome. And lastly, carbon 6. Now, when we move on to the skeletal, remember that since in our original molecule, we only have carbons and hydrogens attached to carbons, we must not draw the carbons or the hydrogens attached to the carbons, okay? So I mentioned to you guys, it is okay with me if you utilize a dot to guide you through the carbon atoms that you may have in your structure. So the first thing that we draw is going to be our parent chain, which is 1, 2, 3, 4, 5, 6 carbons in length. Carbons 2 and 3 are the ones that are going to have the carbon-carbon double bond, and you can even number this so you don't get confused. So between carbons 2 and 3, you have a carbon-carbon double bond. Then, as you can see, on carbon 3 and on carbon 4, we have substituents. Since they're only 1 carbon, you're just going to draw a line and put a dot. Now, some of you may be thinking, but Dr. Luz, when you look at the condensed structure, the CH3 is pointing up. The only reason why I'm making it point down is because I see that my vertex is pointing down. So that's what I'm accustomed to. Now, if you guys write that methyl on carbon 2, on carbon 3 pointing up, that's okay. You're only taking chemistry 112. As long as you get the substituent in the right position, I'm okay with that. On carbon 4, again, I'm just used to it. So because the vertex is pointing up, I'm going to put that methyl pointing up. And that is the structure for 3,4-dimethyl 2-hexene. Any questions on alkenes? Then let's move on to alkynes. So alkynes, when it comes to naming, very similar to alkenes. But instead of looking at a double bond, we are going to look for a carbon-carbon triple bond, okay? So as you can see, and we have done throughout our discussions in naming hydrocarbons, what is step number one? Finding the longest continuous chain of carbon atoms. But when we have an alkyne, we need to include both carbons that are holding the carbon-carbon triple bond. You can write the alkane name for it, but then the ending, you're going to change ANE to YNE to represent that you have an alkyne. How do we name the atoms? Well, you're going to name the carbon atoms starting from the end that is closest to the carbon-carbon triple bond, okay? We talked about equidistant alkenes. You could have equidistant alkynes. None of the examples that I have right here on the right side express that, but keep in mind that that can happen in alkynes also. If you have an equidistant alkyne, remember that that just means that regardless of the direction of your numbering, your alkyne is always in the same position. Understand that in order to break the tie, you will do the numbering of the substituents such that you will be numbering them from the end that is nearest the closest first substituent. Understand that that's only for equidistant. In general, we want to give the lowest number to our alkyne. As you can see, when it comes to the name, you write the parent chain, which is the longest carbon chain that ends in -ine. We give the position of the first carbon in the carbon-carbon triple bond, and we can now forget the rules for having only one substituent in my alkyne, having two substituents that are the same in my alkyne, or if I have different substituents in my alkynes. Remember that those rules for one substituent, two that are the same, or more that are the same, or different substituents still stand for all the functional groups that we are talking about. So let's go over the first molecule. This is a condensed structure, okay? So I want you guys to take a minute, look at the molecule, and let's find the number of carbons in the longest continuous chain of carbons in this alkyne. And let's put the number in the chat. Great. I like to see those sevens. Great job, you guys. Now, you could select B7, or you could select B7. It will give you the same name, you guys. Okay? So it is easier to highlight this, but understand that either selection is going to be correct. And as you guys said, since we have 7 carbons, on which end are we going to start? On the left or the right? Remember that we have to number from the end that is nearest the carbon-carbon triple bond. I agree with you guys. We're going to start from the left. So this is carbon 1, this is 2, 3, 4, 5, 6, 7. So as I mentioned, we can write the name of the alkane. Since it's 7-heptane, but because we have a carbon-carbon triple bond, we erase the A and E, and we put -ine to represent that we have an alkyne. We have to give the position of the first carbon in the carbon-carbon triple bond, which is a position 3. And then how many substituents do I have? And let's put in the chat, what is the name of that substituent? So for this molecule, how many substituents we have? Oh, great job, Maria. Exactly. I agree with that. On position 6, I have a methyl group. So the name of this compound is 6-methyl-3-heptine. Questions about the first example? Put a 1 in the chat if you're ready for the next example. Excellent. I would like to see more 1s. Let me make sure that people are here and participating. We'll get there. Let's do the skeletal structure, okay? So this is the skeletal structure for an alkyne. I want you guys to take a moment and find the longest carbon chain here. And let's put it in the chat. How many carbons in the longest carbon chain? Ooh, I agree with Katie and with Nikki. I see 7 carbons. Let me illustrate them. 1, 2, 3, 4, 5, 6, 7. Put a 1 in the chat if now you're like, oh, wait, I understand why there's 7. Great. So since we have 7 carbons, this is another heptine. Now, remember, we have to start from the end that contains the carbon-carbon triple bond. So we have to go 1, 2, 3, 4, 5, 6, 7. So I have to get the location of my first carbon in my alkyne, which is a 1, okay? And here I have 2 substituents. What is the name of the substituent that I have on carbon 3? Let's put it in the chat. Great job, you guys. Ethel, what about the substituent that I have on carbon 5? Awesome job. You guys got this. It's a methyl. Now, remember that when we have substituents that are different, we need to put them in alphabetical order. So what comes first? Awesome. The 3-ethyl. So we do 3-ethyl, 5-methyl, 1-heptine. In lab 3B, you guys have more practice when it comes to getting a structure and writing the name, okay? But at least I want to make sure that you guys practice going from name to structure. So put a 1 in the chat if you're ready to practice. Make sure that you check out the in-class worksheet, or you also have lab 3B in order for you to review this concept. Excellent. So let's move on to do the following problem, okay? How do I draw the condensed and the skeletal structure for an alkyne? Similar to what we've done before, you guys, this is not going to change much. We need to always start with the last word, which is the parent chain. So when it comes to the parent chain, let's look at the first one, 4-methyl-1-pentyne. So how many carbons in the longest carbon chain? Excellent. I love to see those fives. So we have 1, 2, 3, 4, 5. Okay. Where is my carbon-carbon triple bond? Between carbons 1 and 2. Then on carbon 4, I have a methyl group. Lastly, I add the hydrogens. So let's at least practice one more time before we move on. I want to see it in the chat. How many hydrogens do I need to add to carbon 1? Excellent job. 1. What about carbon 2? How many hydrogens? Love to see those zeros. What about carbon 3? Oh, you guys got this. Carbon 3 needs 2. What about carbon 4? Awesome, 1 hydrogen. And lastly, carbon 5. Great. So this is the condensed structure for my 4-methyl-1-pentyne. Now, when it comes to the skeletal structure, let me give you guys this disclaimer. Understand that many of the structures that I show you guys are generated through a computer program. And my computer program actually takes into account if something has a particular electron group geometry. So that's why when you look at some of these structures, they may look like a long line, and you guys may be wondering, wait, how many carbons do I have? So for example, if we go specifically, just to give you guys an idea, if we look at some of these structures, which this is the work that you guys have to do for the post lab for lab 3B. So if we look at molecule E, okay, so it may be a little bit hard to see where my carbon's atoms are, and you can see that I highlight them in green. The longest carbon chain in this one is 8, okay? So taking into account that, I want you guys to take a moment and tell me how many carbons are in the longest carbon chain for F. This will help you to complete the post lab anyways. How many carbons? Let's put it in the chat. How many carbons in that alkyne? Excellent job. There's one right here, 2, 3, 4, 5, 6. Let's see, any other alkyne? And I have letter B right there for you guys. So understand that when it comes to alkynes, again, many of my molecules are just generated in computer programs that take into account that alkynes, because they're triple bond, they're actually linear. So please don't be confused with the number of carbons that these alkynes have. Now, when you guys have to write the answers for me for lab 3B, let's understand that specifically for the purpose of chemistry 112, I'm going to show you the correct way, but I'm going to show you guys other acceptable formats, okay? So let's go over the correct way to do this. So in the skeletal structure for this molecule, I'm going to draw the triple bond, which is right here. This triple bond represents carbons 1 and 2, okay? Now, extending out of carbon 2, we have carbon 3. Carbon 3 is still linear because it's been held by the carbon-carbon triple bond. Carbon 3 is the first carbon here that is tetrahedral. So that means that carbon 3, then we can go down to draw carbon 4, up to draw carbon 5, okay? And that's at least the parent chain. Since carbon 4 has a methyl group, understand that then we're going to make a line pointing down, and that's where our methyl group is. This is other acceptable ways that I will take it, just because you guys are in chemistry 112. This is, for many of you, your one and only chemistry class for nursing, for kinesiology, for dental hygiene. If you have to take organic chemistry, like the whole semester or at least one semester of it, understand that the rules that will be given to you there are a little bit more advanced. But for now, for the purposes of this class, if you guys give me the following molecule, you say, okay, Dr. Luz, this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, this is carbon 5. Between my carbons 1 and 2, I have a triple bond. And then on carbon 4, I have a methyl group. I will take this answer from you guys because it's illustrating the correct name that I gave you, but understand that in terms of VSEPR rules, it doesn't look like that, but I want you guys to at least understand where are the carbons, how are they bonded? So I will accept that second structure. Any questions going from name to structure for alkynes? Put a 1 in the chat if you want to see one more example going from name to structure. Great. I'm going to make you guys walk me through it. Let's do the second example, 1-chloro-3-hexane, okay? So first, how many carbons in the longest carbon chain for this name? Let's put it in the chat. Excellent. 6 carbons in a row. 1, 2, 3, 4, 5, and 6. Then we have the triple bond between which 2 carbons? Let's put it in the chat. Which 2 carbons are going to hold? So 3 is the first one. And what is the second one? Thank you, Dominique. Thank you, Katie. Between 3 and 4. Okay, so 3 means that between 3 and 4 is where I have my carbon-carbon triple bond. So if I number this, 1, 2, 3, 4, 5, 6, in between carbons 3 and 4, I have my triple bond. Okay. Then, as you can see, on carbon 1, I have a chlorine. You guys can put it in any direction. You can make the chlorine point up. You can make the chlorine point to the side. As long as it's attached to carbon 1, we're good. Then we fill in the hydrogens. I'm just going to go straight into filling in the hydrogens. So carbon 1 has 2 hydrogens. Carbon 2 has 2 hydrogens. Carbon 3 doesn't need any hydrogens. Carbon 4 doesn't need any hydrogens. Carbon 5 gets 2. Carbon 6 gets 3. Okay. Put a 1 in the chat if the addition of the hydrogens makes sense. There are 15 students here. Let me make sure. I only got 5 ones. I only got 6 ones. There's 9 people that, okay, there you go, 8 people. I just want to make sure that everybody's on point because you guys have this lab that is due tomorrow. Awesome. I got 5 more people out there in the world. I just want to make sure that you guys get this. Now let's do to the skeletal. Again, I'm going to draw it in an acceptable way, even though there's different ways to draw it, right? Let me actually draw both so you guys see the difference between them. So if I draw my carbon-carbon triple bond. This is 3 and 4. Connected to carbon 3, I have carbon 2. And because carbon 2 is tetrahedral, then I can actually show that it's tetrahedral. So I will move it down. Okay. This is carbon 1. And attached to carbon 1, we have the chlorine. Then we move on to the next side. From carbon 4 is connected to carbon 5. And carbon 5 is tetrahedral. It has 4 electron groups. So then I can bend it. And that gives rise to carbon 6. So this is one of the acceptable ways to draw the molecule. The other way that I will accept it from you guys is that you guys go 1, 2, 3, 4, 5, 6. You number your carbon atoms 1, 2, 3, 4, 5, 6. Between carbon 3 and 4, I have the triple bond. And then on carbon 1, you can point it in any direction. You can make it point down or point up like I did there. As long as you put the chlorine on carbon 1, you're good. Put a 2 in the chat if it makes sense. The condensed and skeletal structure for 1-chloro, 3-hexene. Excellent. Just make sure that you practice, you guys. That's the key to success here. Practice, practice, practice. You have some practice problems in your textbook. You have the worksheet that I provide. You also have lab 3B. Okay. Excellent. Any questions? Naming alkanes, alkenes, or alkynes? Awesome. No questions. So let's move on to the last topic in chapter 4, which is isomerism in organic compounds. Okay. So what are isomers, or this whole term of isomerism? It is important to note that there are several compounds in organic chemistry that share the same chemical formula, but they have different arrangement of atoms. And that's what makes an isomer. So this description that you see here is what an isomer is. Now, since these molecules are going to have different attachment of atoms, they're going to have different chemical properties and different physical properties, okay? So what are the types of isomers that you guys need to know? The ones given in this flow chart. Okay, so let's define them. There's 2 major families of isomers. On the left, on the blue box, you guys have what are called constitutional, in other words, structural isomers. So what defines something as a structural or constitutional isomer is that these are compounds that have the same chemical formula and different attachments of the atoms. So before class, I was giving you guys the example, okay, if you have C4H10, you can actually say that butane, which is this, CH3, CH2, CH2, CH3, has the chemical formula C4H10. And if you look at another molecule like 2-methyl propane, which is written as CH3, CH, CH3, CH3, you will say butane and 2-methyl propane are constitutional isomers of each other. Okay? Then the other family of isomers that we have are going to be stereoisomers. In other words, spatial isomers. Those are very interesting because the stereoisomers are going to have the same chemical formula, same order of attached atoms. But different arrangement in space. Okay, so spatially, they're going to have different arrangements. I actually have examples in further slides so we can see them. When it comes to the stereoisomers, as you can see, we are going to have two major families, diastereomers and enantiomers. Okay, so what is a diastereomer? It's going to be cis and trans isomer, and I will explain in a moment what a cis-trans isomers are. Cis-trans isomers exist in alkenes, and even though it's mentioned in the textbook, cyclic alkanes can have cis and trans isomers, but I'm not going to go over cis and trans isomerisms in cyclic alkanes. I'm only going to focus on the alkenes. Enantiomers, on the other hand, I'm going to show you guys in a few moments how, if we have two molecules, how is it that they have the same chemical formula, the same order of the atoms, but the spatial arrangement of it is going to be different. So let's just look at these guys in more detail. Starting with the constitutional isomers. Again, these compounds differ in the way to which the atoms are connected to one another, okay? But they have the same chemical formula. So let's look at these pairs, okay? In the first pair, and we're always going to be comparing two pairs. In this molecule, both of them are C6H10. Let me illustrate the carbons and hydrogens so you guys see them. We have a carbon right here with 3 hydrogens. We have a carbon right here with 2 hydrogens, a carbon right here, carbon right here, carbon right here with 2 hydrogens, carbon right here with 3 hydrogens. Put a 1 in the chat if you can say like, oh, okay, makes sense where the carbons are and the hydrogens. I just want to make sure that you guys are following. Awesome. Let's look at what we're comparing it to. There's a carbon right here with a hydrogen. There's a carbon right here with 2 hydrogens, carbon right here with 2 hydrogens, carbon right here with 2 hydrogens, carbon right here with 3 hydrogens. So when we look at both alkynes, okay, they have the same chemical formula, okay? But we can obviously see that the attachments of the atoms are going to be different. So since the attachment of the atoms are different, you guys, they're going to have a different name. You guys already learned how to name alkynes. Let me just erase the carbons and hydrogens. What is the name of the first alkyne? The one that I just erased the carbons and hydrogens. What is the name of that one? Let's put it in the chat. I agree with the 3, but it doesn't end in ane. We have an alkyne. Great. This is 3-hexyne. What about the alkyne that we have on the right? What is the name of that one? Excellent. This is 1-hexyne. Okay, so at least these guys you can name. Let's look at the next one. Both of these molecules have 4 carbons and 8 hydrogens. Put a 1 in the chat if you want to see those 4 carbons and 8 hydrogens, because I know that there may be some of you that actually helps. Awesome. Let me just write them in. So here we have a CH2, here we have a CH2, here we have a CH2, here we have a CH2. So for the molecule on the left, 4 carbons, 8 hydrogens. Put a 2 in the chat if it makes sense. Awesome. Let's look at the molecule on the right. This is a CH2, this is a CH, this is a CH2, this is CH3. Put a 3 in the chat if it makes sense. The 4 carbons and 8 hydrogens. Excellent. Guess what, you guys? You guys can also name these 2. Because these are functional groups that we already learned how to name. So here on the left, we have a cyclic alkane. What would be the name of the molecule on the left? Name for the molecule on the left. I agree with the butane, but how is that different from? Great. Thank you for putting it in the chat. The molecule on the left is cyclobutane. So the prefix is cyclo. Now, what about the molecule on the right? What's the name of that? It's an alkene. Excellent, 1-butene. So as you guys can see, hey, cyclic alkanes and alkenes, as long as they have the same chemical formula, hey, they actually they are constitutional isomers of each other. Let's look at one more example. Now, this is back from when we started chapter 4. What is the functional group that we have on the left? What is that functional group? Let me write in the carbons and hydrogens so you guys see them. This is CH2, 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 CH2. It's not an arene. The carbon, this is CH2, 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 CH3. When you have a single bond oxygen bonded to two carbon chains on either side, it's not a cyclohexane. Thank you, Vanessa. This is an ether. What about the functional group that I have on the right? What is that? A carbonyl that on either side, it has a carbon chain. What is that? A carbonyl group that on either side, it has a carbon chain. Great. Thank you, Katie and Kiyomi. This is a ketone. So this can give you guys a clue of like, oh, if I have an ether and a ketone and they have the same chemical formula, they are going to be constitutional isomers of each other. So again, the take-home message here is that if you have a pair of molecules, they have the same chemical formula, but they obviously have a different attachment of atoms. In the example above, you guys can name them. In the sample, in the example below, you guys can actually see the structural difference. They are called constitutional, in other words, structural isomers, okay? Any questions about constitutional or structural isomers? Let's move on to the next family of isomers, which are the stereoisomers. I mentioned to you guys, stereoisomers have identical molecular or chemical formulas, okay? But they are not structural isomers because the atoms are bonded in the same sequence, you guys. But the difference is that they are arranged in space differently, okay? So most of the time when we're dealing with stereoisomers, these two molecules are going to be mirror images of each other, okay? But the two images cannot be completely matched, so that's why we call them non-superimposable, okay? And as long as our stereoisomer has 4 different groups around the carbon atom, that is known as a chiral center. Please don't say chiral. You don't study chemistry. That word is pronounced this word, chiral. Okay? So again, what is a chiral carbon? Is going to be a carbon atom with 4 different groups around it. Okay, so you guys can see here, molecule on the left is going to be a carbon atom bonded to a hydrogen, a bromine, a chlorine, and an iodine. What is the molecule on the right? It's mirror image. So we are reflecting. So just imagine that, you know, the molecule on the left is looking at itself in the mirror, and then that's what develops the molecule on the right. Okay. Now, you guys can see that they have the same order of the atoms because we have a hydrogen, a chlorine, a bromine, and an iodine. What happens when we actually try to overlap these two molecules? As you guys can see, we cannot overlap all of the atoms. That's why these are 2 different molecules, okay? Let me turn on my video. Chiral objects are all around us. Maybe you haven't realized it. The classical example for chiral objects, I just turned on my video so you guys can see this. Hands. Your hands are chiral objects, because if you put your hands one in front of the other, you can see that the fingers reflect. But then when you try to superimpose them, put one on top of the other, it doesn't matter which direction, you cannot overlap your fingers. So that means that your hands are a chiral object. Your feet are chiral objects, because that's why we have a left shoe and a right shoe. And then if you put the right shoe in the left foot and vice versa, you start walking funny, or it feels very uncomfortable. Why? Because these are chiral objects. They're mirror images of each other. There are non-superimposable because they don't line up completely. Okay. And chirality, you guys, is very important in biochemistry. So I just wanted to illustrate that. Chirality is all around us. Now, whenever you have this situation, which means, okay, I have two molecules. The molecule on the right is the mirror image of the molecule on the left. This partnership is what we call enantiomers. Okay, so whenever we have that situation, then we say that we have enantiomers. Okay, now, when it comes to this, I want you guys to be able to, if you're given a molecule, find where the chiral centers are for a specific molecule. So let's actually practice finding the chiral centers in a particular molecule, okay? Whenever we're looking at chiral centers, we always do it in terms of carbons. So the first thing that I'm going to do, given the skeletal structure, is writing the carbons and hydrogens. So I'm going to use a different color. This is a CH3, this is a CH, this is a CH3, this is a CH, this is a CH3. Okay? Now, as you can see, we have the potential of 5 different chiral carbons in this molecule. Put a 1 in the chat if that part makes sense. Well, I have 5 carbons, so maybe I have the potential of 5 chiral centers, okay? All I'm saying is, if you have 5 carbons, you have the potential of 5 chiral centers. But as I just mentioned, a chiral center is going to be a carbon atom that specifically has 4 different groups around. It has to be all different atoms, okay? If I label this, you guys, as A, B, C, D, and E, by looking at the molecule, who are we going to disqualify in terms of chirality? Who's not chiral? Let's put the letters in the chat. I agree. E, good. C, awesome. Who else? Like straight out of the gate. C and E, I agree. A, excellent. Because why are we disqualifying them? Because they have 3 hydrogens. So guess what, you guys? Whenever you see a CH3, say, oh no, that's not a chiral carbon. Whenever we see a CH2, same thing, not a chiral carbon. So now it's a matter of saying, is B and D chiral carbons? Let's explore first B. When it comes to the carbon on B, it is bonded to a CH3, it is bonded to a CH3, it is bonded to hydrogen, and it is bonded to this carbon atom. So by the definition, is B chiral or not chiral? Excellent job, not chiral. For those of you that are like, wait, I don't see it. Carbon B is bonded to 2 methyl groups in essence. Technically, if you name this, you cannot see them as methyl groups. But for now, for the purposes of chirality, you will say, you know what? Carbon B is bonded to the same thing on either side, which is a carbon with 3 hydrogens. Okay, let's explore now carbon D. In carbon D, we are bonded to a hydrogen. We're bonded to a bromine. We are bonded to a CH3. And we're bonded to this whole thing. Because remember, it's all of that area that has been held by that single bond. So what about carbon D? Is that chiral or not? Yes or no? Love to see those yeses. So in this molecule overall, the only chiral carbon that I have is going to be letter D. And chiral carbons, we label them by putting an asterisk by them. So that's the only chiral carbon that we have in this molecule. Let's move on to the next example. Okay, I'm going to write in the carbons and hydrogens. This is a CH3, this is a CH2, this is a CH, this is a CH3, CH2. Okay, put a 1 in the chat if it makes sense, the carbons and hydrogens that I wrote in. Awesome. So in this molecule, we also have the potential of maybe having 5 chiral carbons, right? Now, if I label these with letters, and let's say that this is A, B, C, D, E. This is just arbitrary, labeling. You can label this with numbers, with letters, with whatever you want. I just choose letters. Straight out of the gate, which ones are not chiral? You guys got this. You got the first one. You guys can get this one. Excellent. 8 is not chiral. Who else? I agree. E is not chiral. I agree. Katie went all in. Great job. A, B, D, and E. All of them are not chiral because they have 2 groups that are the same, which is the hydrogens. So by now, you guys should know that if you have a molecule, you write in the carbons and hydrogens, any CH3, any CH2, not chiral molecules. Let's now investigate carbon C. Carbon C is bonded to this hydrogen, is bonded to this area of the molecule, is bonded to this area of the molecule, and lastly, is bonded to this area of the molecule. So is carbon C chiral? Yes or no? Great to see those yeses. So what are we going to do with carbon C? We're going to label it with an asterisk. So this molecule has 1 chiral carbon. I want you guys to take a moment and do letter C. I'm going to write in the carbons and hydrogens for you guys. Let me put letters by them. Now that we have the carbons and hydrogens, take a moment, use the rules that we just discussed, Put in the chat, what is or are the chiral carbons in this molecule? Oh, Maria got it right away. Awesome. Let me see who else. Katie agrees. I agree with both of you guys. Dominique got it too. Awesome. Vanessa got it. Isaiah got it. Put a 1 in the chat if you guys want me to label C and D so you see the different groups. Awesome. So let's just talk about why A and B are not chiral. A and B, you guys, do not have 4 different things. So that's why disqualified. E and F disqualified because they have, one has 2 carbons, the other one has 3. So when we look at letter C has the hydrogen. It has this whole thing of the molecule through this bond is bonded to the OH. It is bonded to this whole thing. So those are the 4 bonds on letter C, or the 4 things that are attached around it. So again, I'm going to draw an asterisk around C. Next, let's look at D. Carbon D, I agree. This is also a chiral carbon. What are the things attached to it? An OH through this bond, a hydrogen, this whole thing to the left, and then this whole thing to the right. Okay, so as you can see, this molecule has 2 chiral carbons. Okay, any questions on the chirality of carbons within a molecule? Great. Then let's move on to the next topic, which is cis and trans isomers. Okay. Now, cis and trans isomers, you guys, let me specify, please just know it, get it in your brain. That concept only pertains to alkenes. Those are the only molecules, or in other words, unsaturated hydrocarbons that will have cis and trans isomers. So where does the idea of cis and trans isomers comes from? You can see here that we have the following molecule, 1,2-dichloroethene. We can see that both chlorines can be pointing up, so in the same direction in the molecule. Okay, if you have 2 things pointing in the same direction, that is called a cis arrangement for your alkene. If you have 2 groups, depending on their priority, we will talk about their priority soon, they are away from each other on opposite directions. See how the chlorine is pointing up on the left, but then the other one is pointing down on the right? That is called trans, because they are in opposite directions. These cis and trans notations are also known as Z and E notations. So just in case, if you're like, oh wait, I don't know the cis and trans, E and Z notations is the same thing. The E and Z actually, the E and Z comes from German words. Z is in Gagen, And then E is entgegen, which means same side or opposite sides, okay? That's where E and Z comes from. But for the purposes of the class, we're just going to call it cis and trans. So why is this important? You may have noticed, for those of you that already opened the chapter quiz for chapter 4, that when it comes to alkenes, we need to determine if a particular alkene is cis or trans, okay? And that is incorporated in the name. So it is important for me that you guys understand how to incorporate cis and trans into the name of alkenes. So let's say that we have the first molecule, okay? When we look at this first molecule, and again, I'm going through the naming a little bit, faster, just because we've been practicing naming. Longest carbon chain here is going to be this one, okay? Which is 1, 2, 3, 4, 5. So this is going to be, in terms of the name, this is pentene, this is 1-pentene, this is 1,2 difluoro 1-pentene. Now, the question is this cis or is this trans? When your two substituents are in between carbons 1 and 2, it's a little bit easier to see cis and trans based on the rules that I just gave you guys. Is this cis or trans? Are they pointing to the same direction or different directions? Great job. This is going to be trans. And we just put it before the alkene name. Sometimes this cis and trans is not as obvious here. Again, it's trans because you can see that one fluorine is pointing up while the other fluorine is pointing down. Alkenes don't have the ability to rotate, so these guys are locked in this configuration. So what happens if you have, for example, this molecule, where you do not have two halogens? And then you have to determine, ooh, what is this cis or trans? Well, let's go over the naming. This is my longest carbon chain. This is carbon 1, right? Carbon 1, carbon 2, carbon 3, 4, 5, 6. This is 2-hexene. And then this is 2-bromo. Okay. How do we determine if this is cis and trans? Well, we have to look more closely at the molecule. And this is what we need to do, you guys. You're going to take your alkene and you're going to split it in half. Okay. And then we're going to prioritize the groups that are bonded to each of the carbon atoms that are held by a double bond. So remember, there's a carbon right here that is bonded to a hydrogen. There's a carbon right here that is bonded to a bromine and is bonded to a CH3. So if we look to the left of the molecule, okay, we see that carbon 2, which is one of the carbons in the carbon double bond, is bonded to bromine versus carbon, because that is what they are directly attached to. So this carbon is attached to bromine on one side and carbon here. Let me ask you a question. Which one has a higher atomic number? Bromine or carbon? Look at the periodic table. Who has a higher atomic number? Thank you, Dominique. Bromine. So how are we going to label bromine? We are going to label it as high atomic number or high priority group. What does carbon in that area get? The label low. because it has a lower atomic number compared to bromine, okay? Put a 1 in the chat if the high and low labels make sense for the substituents or the things that we have next to carbon 2. Let's move on to whatever is attached to carbon 3. On carbon 3, we can see that when it comes to what they're attached to, carbon 3 is directly attached to a hydrogen pointing up and to a carbon pointing down. Let me ask you the same question. Who has a higher atomic number? Carbon or hydrogen? Let's put it in the chat. Higher atomic number. Great, carbon. So that means that I'm going to put to that bond pointing down high, and the hydrogen is going to get a low label, again, based on atomic number. Let me ask you this, you guys. Now let's look at the view from left to right. If I look at this molecule in the labels, let me just redraw it because that makes it a little bit easier. I have a carbon, double bond carbon. This is how it looks like. Low, low, high, high. Okay. My lows and my highs are pointing in the same direction, meaning the lows are together and the highs are together. Okay, put a 2 in the chat to see if that makes sense. Again, the 2 lows are pointing up or the 2 lows are pointing down. Let me just turn on my camera. So cis is when we have this. I always say that when you're determining cis and trans, it's like cheerleading. This is cis while this is trans. So opposite is trans, this is cis. So when we look at this, my lows are pointing up, the same direction. My highs are pointing down, the same direction. I mentioned to you guys that if you are in the same direction, is this cis or trans? If you're in the same direction, great. So that means that this, the correct name for this molecule is cis 2-bromo-2-hexene as given drawn. Okay. For those of you that are curious, how would the trans look like? Let me just draw it. You can prove yourself at home that what I'm drawing now is the trans of this. This is trans. So utilizing the same idea, you can actually prove that that second molecule that I drew is the trans version of 2-bromo-2-hexene, okay? We have 5 minutes left. Put a 1 in the chat if you're ready for one more example. Excellent. Let's name the following molecule. Let's find the longest carbon chain. There you go. This is the longest carbon chain. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this is 2-octene. This is 3-bromo, 2-chloro, 2-octene. Okay. We have to determine if this is cis or this is trans. Okay. By just looking at it, you can even tell if you have halogens, okay? Because halogens have a higher atomic number than carbons. It's really easy to tell. So is this cis or trans? Great job. Trans. We can already tell that this is trans. Let me show you why they're trans to wrap up this topic. We cut the molecule in the middle. We include the carbons and hydrogens. There's a carbon right here. There's a carbon right here with 3 hydrogens. There's a carbon right here. There's a carbon right here with 2 hydrogens. If we look at carbon 2 is attached to chlorine versus carbon. Chlorine has a higher atomic number. So we are going to put the high label. Carbon, because it has a lower atomic number, we're going to put the low label. When we look at what is attached to carbon 3, we're comparing the carbon to the bromine. Bromine has a higher atomic number. So this will be the high label. This will be the low label. So if I redraw this to at least make it more clearly, we will notice that in that double bond for carbon 2 and 3, we have high here, low here, high here, low here. You guys see how the highs and lows are not pointing in the same direction? Because when we look at this from left to right, look, high, low, high, low. So that's the reason that this is trans. Because the high priority, meaning in terms of atomic number, and the low priority groups in terms of atomic number are in different directions. Any questions when it comes to determining cis and trans in alkenes? Great. Make sure that you check the in-class worksheet for chapter 4, because one of the problems that I didn't do here, but I want you guys to be able to do, is that if you are given a pair of molecules, to distinguish if they are constitutional isomers, enantiomers, diastereomers, or identical molecules. So make sure that you practice that in the in-class worksheet. And if people have questions about that, I am more than happy on Thursday to go over that problem, because you guys actually have a problem like that in the chapter quiz. Since there are no more questions, then that is all for today.